Hello, I'm going to talk to you today about the physical metallurgy of zirconium alloys. Now, metallurgy is a very broad field, but fortunately it can be broken down into two main parts. One is physical metallurgy and the other one is chemical metallurgy. And the physical metallurgy is distinct from chemical metallurgy in that it deals with the physical properties of materials, of alloys, of metallic alloys. And the main ones of interest for use in nuclear reactors being elastic and plastic deformation, yield and tensile strength, fracture behavior, and also the dimensional stability of materials. That's radiation, certainly during radiation creep and growth. Now, chemical metallurgy deals more with corrosion, and that's a very broad area itself, and I will not be covering it in this talk or in this series of talks. So let's continue by introducing first a list of properties of zirconium. I've lifted this table, or sort of modified from a table generated by a guy called Tricot, worked for CSIS in France, and he wrote a paper essentially looking at hafnium, but he was comparing hafnium with zirconium back in 1982, and this was a nice summary of listing of all the more important physical properties, Young's modulus, for instance. There are a lot of electrical properties that are covered here, but that doesn't apply to use of zirconium alloys in nuclear reactors, so I won't be touching on these. I put this table here just for reference if anybody cares to look up key things, but of course you can go on the internet, look on and look up any of these properties or any subject area, limited subject area in the field of physical metallurgy of zirconium alloys. Now, we're mainly interested in the use of zirconium alloys in nuclear reactors. So I want to start by looking at the neutron interactions with zirconium. And in this table, you'll see here a value for the thermal neutron absorption cross-section. This energy here corresponds with room temperature, and that's because most of the measurements that allow one to determine a cross-section are made at room temperature outside of the reactor. A beam line will come out of a reactor, and one can use various methods of counting neutrons to determine what the cross-sections are. And as you'll see, zirconium compared to titanium and hafnium, which are all in the same group in the periodic table, hafnium being heavier than zirconium, zirconium being heavier than titanium. Zirconium has a very low thermal neutron absorption cross-section. So let's talk about neutron interactions, not just the thermal neutrons. Our zirconium is used in nuclear reactors primarily because it has a very low thermal neutron absorption cross-section. In a nuclear reactor, of course, we want as many thermal neutrons around as possible. We don't want to be absorbing them, and we want to maintain the fission reaction, especially if one is talking about reactors operating with natural uranium fuel, non-enriched fuel. So for natural uranium reactors, it's particularly important to use zirconium alloys in the core so that one doesn't minimizes the amount of absorption. And zirconium is an ideal element because it has other properties which make it suitable for being a structural material. And if you compare the neutron absorption of zirconium with most common structural materials, materials that are used in steels, for instance, you'll see that it has a low thermal neutron absorption cross-section, and that's one of the reasons why it was chosen as the element of choice for creating alloys for use in the nuclear reactor core, especially for fuel cladding. Now, I've highlighted here also hafnium. Hafnium is an impurity in zirconium, in zirconium ores, roughly about 2%, but it has an extremely high cross-section. So when refining zirconium, it's important to get the hafnium reduced as much as possible. So for most specifications, STM specifications for alloys used in nuclear reactor cores, the hafnium, the allowable hafnium, is generally about 100 weight ppm. We don't want to be absorbing too many neutrons, and so the hafnium, reduction of hafnium, which is chemically very similar to zirconium, is important as part of the fabrication process. Now, some of the ANT presentations that have been given in previous years talk about fabrication of zirconium alloys, and there it's explained how hafnium is separated from zirconium. So if we look at the N-gamma, which is N-gamma neutron cross-section, that's basically the probability that a neutron will interact with an atom of a particular isotope of a given element. I've got a plot here showing as a function of neutron energy. Here we have 1 MeV, it's the high energy neutrons, which you're probably all familiar with, but the neutrons of interest when it comes to nuclear reactions, of course, sustaining the fission reaction, are the thermal neutrons. And zirconium is particularly good because here, this bottom line here, it has a very low N-gamma cross-section. And I've plotted here the values for the zirconium 90, the zirconium 90 isotope. It is at a very low cross-section of 0.011 barns. Now, in the table from TRECOR, I quoted a value of 0.0185 barns. Oh, I should mention this cross-section is the value essentially at room temperature, which is this dotted line here. So at this dotted line here, we have the cross sections, and we can compare different elements. In the values at the same energy in the table I showed for TRECOR, zirconium, the average cross section for zirconium was 0.185 barns, which is still low relative to the other elements, but most of that 0.185 comes about because of this isotope, zirconium 91, and that basically results in a higher average cross-section when one averages over all of the isotopes in zirconium. So the N-gamma cross-section for zirconium is low relative to all other elements that one would typically see in a nuclear reactor. We can't talk about neutron interactions without talking about radiation damage. Now, one of the issues when using different alloys in nuclear reactor cores is the effect of the neutrons causing atomic displacement. And by far the most common way in which atoms are displaced is by direct collision with energetic neutrons. A high energy neutron comes in, collides with an atom, the atom is displaced, and it then displaces other atoms until its energy is dissipated below its threshold energy, or in a nominal value, 2 times threshold energy. When you get to energies below that at the end of the collision cascade, those energies, any new displacements don't create any additional numbers of interstitial atoms, because an atom would, at that point, that might displace another atom, would basically then take up its position in the lattice. So we have these simple expressions for atomic displacements, and there's a limit for the energy of the atoms, of the displaced atoms, which we call T. T in this case is the energy of the primary knock-on atom, but it also applies to at the point at which atoms would stop being displaced in a collision cascade. Now, the determination of T is simply based on transfer of momentum, and basically it's a geometrical consideration for the transfer of momentum, where one resolves both the momentum and while conserving the kinetic energy. So the cross sections one has for atomic displacements are a function of this angle and so we have a whole range of possible energies that are possible to be produced for a given neutron, initial neutron energy. The energy of the T in the pKa, you have a range of possibilities. And what that means is that for any one neutron of a given energy, you have a range of primary knock-on energies, what's called the primary knock-on atom energy distribution, the pKa distribution. But let's think about the minimum energy. And the minimum energy one would need to create a displacement comes about when we have a direct displacement, where basically theta it's a direct head-on collision, theta 0 in that case. And what you have here is an expression which gives the transfer of momentum. So because the neutron is a very low mass, 1 atomic mass unit, compared to something like nickel, which is some in the region of 58, because of this transfer of momentum, you need an energy of the neutron to be at least 600 eV, roughly, in order to create a displacement. And that only occurs for those few displacements or few collisions where there's a direct collision. In the case of zirconium, because zirconium is a very much heavier element, the energy of the neutron needed to displace just 1 zirconium atom the minimum energy is 900 eV. So whereas fast neutrons are the most common method of creating damage in material, in alloys in the reactor core, it's not the only way, and there are many other different ways in which atoms can be displaced. So what about thermal neutrons? If we have, instead of having a fast neutron, if we have a thermal neutron, what happens? Well, what happens when a thermal neutron, which is a very low energy, insufficient to cause any displacements by direct collision, when you have a thermal neutron floating around, it might be absorbed by an atom, and when the atom absorbs a thermal neutron, various reactions can occur. And one of the more common reactions is the N-gamma reaction, in which a gamma ray a gamma photon is emitted. And that gamma photon can have energies of MeV, of the order of MeV, depending on the atom, the isotope in question, and the reactions that one is talking about. And when the gamma photon is emitted, there's a recoil, and that recoil itself creates a number of atomic displacements, typically about 4 or 5. I'm not going to talk about it in detail here, but one of the things that you might hear about in your work is the role of nickel and the effect of thermal neutron absorption. For nickel, nickel is particularly important because it has a high N-gamma cross-section. Most of the isotopes in nickel have high values for the N-gamma cross-section. But more importantly, when nickel absorbs a neutron, it transmutes, it becomes nickel-59. And nickel-59 itself has a very, very high cross-section, the probability of reactions to give alpha, proton, and gamma reactions. And this enhances the damage. So if you have a high thermal neutron environment and you have a lot of nickel, then you're going to get a lot of transmutation to nickel-59, and after a few years you'll get sufficiently high nickel-59 generated that it can have a profound effect on the damage production. And probably more importantly, one of these reactions is the N-alpha reaction. With that occurs, it's normally a high energy event, but in the case of nickel-59, you get this N-alpha reaction that occurs with the thermal neutrons as well. So if you have a high thermal neutron flux, you're going to get nickel-59 produced, but then you're going to get lots of reactions with nickel-59 itself, and some of these reactions produce alpha particles, which is helium, and that then leads to enhanced swelling and helium embrittlement. Okay, so one can look at absorption cross-sections, look at the effect of neutrons in creating displacements by whatever reactions that one wants to consider, whether it's an N-gamma, an N-alpha, an NP, whatever, and also the direct displacements that occur by elastic collisions, elastic and inelastic collisions. There may be some energy lost when the neutron collides with the atoms. But the high energy, at high energies, we get a lot of displacements, a lot of damage produced by direct collision events. And what I've done here is plot the damage cross sections for common elements that are used in alloys in the reactor core, and on this axis I'm showing the cross sections, the neutron spectrum, and I've just limited it here to the PWR. PWR in the mid-core region. This is a measure or an indication of the neutron spectrum in the mid-core region, but at the periphery we have a different reduction in the neutron flux. But what I want to point out is that at the periphery we have a much higher thermal neutron proportion. In comparison, a fast reactor has basically zero thermal neutrons. So any of these absorption reactions with thermal neutrons in a fast reactor we don't consider, and therefore the kind of nickel-59 issue is not as important However, fast neutrons also create helium. So one can demarcate the damage. This is a damage cross section now. This is where we've calculated, or somebody has calculated, what the probability of displacing an atom is for every neutron. And it's not just the probability of a reaction, it's a probability of how many, that gets multiplied by the number of atomic displacements that occur for each reaction. So we have what's called a damage cross section. So in this region here, below the threshold for the minimum transfer of momentum by neutrons, which, as I showed you earlier, was between 600 and 1 keV, roughly. 600 for nickel, 900 for zirconium. In this region, the displacement reactions are mostly from the N-gamma events, whereas in this region here at high energies, this dotted line here being 1 MeV, at high energies, it's the elastic collisions that create most of the atomic displacements. So even though the atomic recoils, any given reaction only produces a few displacements, the cross-section is still comparable to most of the mid-energy neutrons, elastic collisions that you get with mid-energy neutrons. But once you get high-energy neutrons, such as 1 MeV, 1 MeV neutrons, there can be hundreds of atoms displaced in the cascade, of course, depending on the each particular interaction. I touched on helium production by the N-alpha cross-section. Alpha is a helium nucleus. And so it's worthwhile pointing out one other thing, which is interesting for zirconium. So although zirconium was selected because of its low N-gamma cross-section, it's also fortuitous that zirconium has, for most of the energy range, for most reactors, zirconium has basically zero N-alpha reaction probability. So the probability of creating alpha particles, helium atoms with zirconium, you generally have to be at very high energies, and most power reactors don't operate in this energy range. So for the most part, zirconium does not suffer from swelling or helium embrittlement. And just for completeness, I put here the cross-section for nickel-59 that I mentioned earlier. And as you can see, once you generate nickel-59, the cross-section for helium production is extremely high for nickel now compared with other elements. So I guess on the plus side, the lighter side, it takes quite a few years to reach the maximum amount of nickel-59 from burn-in and burn-out. But in a Kennedy reactor, that only takes 5 years, and you produce your maximum amount of nickel. About 4% of nickel-59 is produced, 4% of the nickel-58, which is the most common isotope. And I've actually scaled these cross-sections based on the isotopic abundance. So you can see how even when scaled, if you have nickel-59 around, at the maximum production, at the peak value, the steady state value of the nickel-59, the maximum amount you can get, there is a very high probability of creating helium particles from the at low energies. So if you have a high thermal energy reactor such as Kennedy reactor, watch out. You really don't want any nickel in your core, because these thermal neutrons are going to generate nickel-59 very quickly, and that nickel-59 is then going to react very quickly to create a lot of helium. So nickel components in Kennedy reactors are only used sparingly in specialist components, springs for instance, but even at end of life, this can be a real issue, a real problem. For the PWR, for instance, and BWRs, it takes between 25 and 30 years to reach the maximum amount of nickel 59 being produced. So in most fuel assemblies, which only reside in the core for between 4 and 6 years, it's not as big a problem, but it's still something that one has to take consideration of. Oh, that's just summarizing what I've just said. Okay, let's move on now to crystal structure. It's my favorite subject. As you all probably know or have heard before, or you probably heard it often, that zirconium is a hexagonal close-packed material. What does that mean, hexagonal close-packed? Well, close packing is basically a way of describing, if you have atoms, what is the minimum volume that a given number of atoms can be packed into. And often one uses spheres as an approximation, like I use ping pong balls, as you'll see. And the minimum volume for a given number of atoms comes about by close packing spheres in what's called, in this kind of hexagonal arrangement. Now, a face center cubic material, which has a different crystal structure, is also a close packed structure and is different from a hexagonal close packed material, even though it's close packed. And I'll explain what the difference is now. And all you need to know is that the body center cubic, which I'm not going to be talking about here, very little anyway, is a more open structure. That's good for diffusion if you want to diffuse through the BCC material, but it is not close packed, and that's because the inner orbitals of the elements that comprise BCC material, such as chrome or iron, in their raw state, they create this bonding. Even though it's a metallic bonding, they influence the way in which the atoms will sit in a low energy state. So let's get on to what's the difference between HCP, zirconium, and FCC, which is any austenitic alloy, mostly nickel, but most steels are also FCC because of the nickel addition. If you have sufficient high level of nickel above typically 12%, you can have a substantial amount of FCC phase. The nickel stabilizes the FCC phase, and whereas iron would normally be a BCC structure, when you have nickel there, the common phase is austenite, and of course in nickel alloys themselves it's austenite. So what's the difference between a hexagonal metal and an FCC, a face center cubic metal? So it comes down to the stacking. So I mentioned how close packing is a way to describe the crystal structure, and what you do is you consider atoms to be spheres. It's an approximation, and any material is going to minimize its volume energy density, if you like. The bonds are going to want to be as small as possible. So one gets the optimum low energy configuration being one way you pack together spheres in the lowest or the densest configuration. And it happens to be, for a single plane, it happens to be this hexagonal arrangement here. So the difference between HCP and HEP and FCC is the stacking sequence. In the HEP, it is ABA, and in the FCC, it's ABC. Now, what do I mean by that? So let's start by looking at a layer of atoms. So and this could be in an FCC structure or HEP structure. We've created our first layer. Where can I put my next layer of atoms if I'm stacking this up into some three-dimensional shape or structure? I can put my next layer of atoms here, or I can put them here. So let's call the second layer the B layer and call the first layer the A layer. I could have had my next layer positioned here or here. So these are the low energy sites sitting on this initial layer. And if I choose that as my B layer, then that constrains all other atoms of the next layer up to sit on particular sites. So on this site as opposed to this site, because there's no room for an atom to sit on this site once you have an atom here. So having constructed the second layer, what about the third layer? Now the third layer can actually sit between the B layer atoms and directly above the initial layer, the A layer atoms, as we see here. Or it can sit there, in which case it would be, the stacking would be, this third layer of atoms does not sit directly over the first layer. It sits in the C layer, and then it would be called an FCC structure. Once you've decided you're going to have an FCC structure, then that dictates where all the other atoms sit from that point on. I have to address a little bit of crystallography and symmetry just for completeness. Some of you may appreciate this, some would just would switch off a little bit. But how are the atoms arranged in the HEP structure? Well, this is typically how one would describe the crystal structure or the symmetry of a crystal structure. And the unit cell is actually the smallest arrangement of atoms that can be translated to produce the whole crystal is actually this rhombohedral biprism, or rhombohedral prism in this case. The point I want to show you here is, here we have the atom positions relative to some base origin, and then here, although the next atoms here are here, here, and here, the next layer, which is halfway up the unit cell, or halfway up what's called the C-axis of the unit cell, it sits here, and that's that intermediate site. So this would be an A, and this would be a B atom. And we see the hexagonal symmetry here reflected just at this point here. There is also a hexagonal symmetry from the original layer, but in terms of when you have a unit cell, how do we describe that in terms of symmetry elements? I'm going to just make this statement and then leave it from here. One of the most important symmetry elements that describes a hexagonal close-packed method is the 6-3, is the primitive 6-3 screw. This is to do with space group determination, and it's a way of defining what the crystal structure is based on symmetry. And the symmetry in this case involves not just rotational symmetry, but also translational symmetry. And the thing that defines hexagonal close packed, this 6-3 notation here, relates to this symmetry element. And what that means is that it's a 6-3. What that means is that if we have 6 rotations before we get back to our original position, so 60 degrees for each rotation, at each rotation we translate upwards along the axis on which the symmetry element lies. We translate upwards by 3/6. So we go up half a lattice distance. So if this is my c-axis, I then move upwards by half of that. So we go from this atom, we rotate 60 degrees, we move up half, we're there, we rotate 60 degrees, we move up half, and then we go from an A layer to a B layer and back to an A layer again. B layer, A layer, B layer, A layer. And that way, just with that simple description of the symmetry of this basic unit cell, which is this rhombic prism, one can describe everything one needs to know about the hexagonal system. So, and then once you've defined the symmetry of each unit cell, one can then translate and create the whole crystal. One of the things I showed here, I didn't mention, is that the unit cell, I have talked about the c-axis, the length of the unit cell, and that's the axis which is perpendicular to the initial layer of atoms one establishes, what's called the basal plane, the base layer that defines the stacking of the atoms on everything on top of that. The ratio of this axis, this long axis, what's called the unique c-axis, and the a-axis, which is the distance between the atoms in the plane, in the basal plane, varies depending on the element. For zinc and cadmium, we have an elongated hexagonal prism, and for other metals like zirconium and titanium, we have a squashed prism. It's still hexagonal, but because of the different electronic structures of the different elements, we have slightly different C/A ratio. I guess this shows the hexagonal prism here if you wanted to extract it. And the hexagonal prism in zirconium consists of 3 unit cells. So as I said, we have this arrangement where the stacking or the density of the atoms on given planes varies depending on the element. And how do we define what the crystal structure? You do this with respect using an axis system. In this case, for example, the common one would be a Miller indexing system. So that would then help you define what plane or what direction we're looking at. And for hexagonals, this would be a typical Miller indices. So we'd have A1, A2, and A3, which is the c-axis in this case. Now, problem with Miller indexing, which really still captures the hexagonal symmetry, if we have our A1 and A2 axes, which are separated by 120 degrees, they don't have to be Cartesian, they don't have to be right angles. But the problem is when we index a system like that, if we look at the indices which describe a particular direction, or more importantly, a plane, the plane is the value which is defined by the direction which is perpendicular to the plane, and I'll show you a little bit about that in a minute. This dotted line is a plane in the hexagonal cell. I guess I can draw this out a little bit better. But this has an indices of 010 in the Miller system, whereas another plane here, the green dashed line here, has indices of 110. It's got 1 unit of A1 and 1 unit of A2 in ratio, whereas the perpendicular to this first plane has only A2, O1, O. And that's a problem because you may get confused if you're indexing essentially what is the same plane. This is the pyramidal 2 plane. So there's another system of indexing directions and planes in an hexagonal crystal, and that's the Miller-Brave system. Now in the Miller-Brave system, we create 3 axes, A1, A2, A3, and in addition we have the C-axis, which is normal to the paper here, and we label, or we define directions according to this 3-axis system. And this just explains how the Miller indices, these the small letters here, are related to the Miller-Brave indices. And what that means is that equivalent directions or planes, in this case x1 or x2 or x3, they have the same combination of indices. And this can be defined by, this can be used to define a slip direction or a slip plane. So planes are very important. I'm going to be referring to various types of planes and the Miller-Brave indexing. All you need to know is that how do we define what the index of a plane is? Well, if we take this plane in the hexagonal cell, for instance, it's a 1/1 plane. We look at the intercepts with respect to the different axes, and I've actually put the C-axis here now, even though this says Z. So we look at where this plane intersects, starting from an origin, intersects with each axis. In the A1 case, it intersects here. In A2, it intersects, sorry, not A2, that'd be A3. It intersects at minus A3, and it doesn't intersect the A2 axis at all. So the way you define what the plane is by this method. You take the reciprocal of these intercepts, and then you reduce it all to a common indexing where each indice is a whole number. So you have to scale it depending on if you have a fractional indices. We just scale it so that the whole system is based on a whole number. Normalize it for that in that way. Okay, let's move on to alloying. There are different crystal structures. Oh, not crystal structures. There are different microstructures for zirconium alloys. So even though you want to keep the alloying additions quite small, when using zirconium alloys, one basically adds only small amounts of other elements to strengthen or improve the corrosion of the zirconium. Depending on the thermomechanical processing and the alloying addition itself, one gets very different microstructures. Now, here's an example of a recrystallized annealed zircaloid 2. That there is a twin. I'll talk about twins later. And here is an example of a typical cold work stress relief annealed material. So most cold work materials are stress relief annealed to reduce any residual stresses. In this case, I'm showing an example with zircon-niobium. Basically, the alpha phase, which is the hexagonal phases here, but there are residual amounts of metastable BCC structure, and I'll talk about that further on. But the typical structure of a cold work stress relief annealed material, whether it be zircon-niobium or whether it be zircaloid type material, it tends to be more flattened grains with a high dislocation density, as you can see here. So there are various alloys that are used and defined in the, or basically defined using ASME code, but also the ASTM standards with a UNS number, a universal numbering system, and zircaloy 2 and zircaloy 4 are shown here, zirconium is shown here, and these are the compositions. There are other alloys used in foreign reactors. E110 is used in the Russian reactors for the fuel cladding. And is it fuel? Yeah, I guess they're using fuel cladding. Because in Russian reactors, Zirc 2.5 niobium is the main pressure tube material. But Zerlo is a more recent innovation from Westinghouse, I think. M5 comes from Framatome. Although you can specify the main alloying additions, and as I said, you typically don't want a high level of alloying to minimize the neutron absorption. But what's important is that one also specifies what the maximum impurity level is in the zirconium alloys. And this is particularly important when it comes to hafnium. So these values are in weight percent, and so the hafnium here is given as basically 100 weight ppm is, I think that's 100 weight ppm, yeah. And yeah, so basically you want to minimize the amount of hafnium in your alloy for use in nuclear reactors. Not so for if it's not nuclear, but you want to minimize the amount of hafnium. Another one that you want to have little of is boron, and that is basically 1, 2, 3. It's basically is a very low content. It's 0.5 weight ppm of boron. Boron is particularly nasty because it produces helium, and it has a very, very high thermal neutron absorption cross section as well. So boron would be bad to have. Okay, just for completeness, I'm going to put in the phase diagrams. This shows the phase diagram showing where ZR2NiFe is the most common element, precipitate in the zircaloy. That's BCT, ZR2NiFe. Common precipitate in zircaloy 2 and zircaloy 4 is based on ZrCr2, which is the hexagonal close packed Lavies phase, typically iron substitutes for the chrome. As opposed to chrome substituting for iron, because in the Lavies phase in the iron phase diagram is actually FCC. So the chrome in the zircaloys dominates what the crystal structure is of these precipitates. So this is the composition of zircaloy 2 and zircaloy 4. The main precipitates are C14 Lavies phase and body-centered tetragonal ZR2NiFe. What about zirconium? Well, zirconium is extruded, or when it's produced as tubes, you extrude it at high temperatures, and as the material cools, it hits what's called a monotectile point here, and at that point, any further cooling, because the transformation is sluggish, the zirconium, by the time you get down to reactor operating temperatures or even room temperature, it's in a metastable state, and you have to heat treat it in this region between 300 and 600 degrees centigrade in order to get it to an equilibrium state. very important for the CANDU reactors because pressure tubes are made from zinc niobium. So we developed this TTT diagram, that's temperature time transition diagram for zinc niobium pressure tubing. So this is where you have the beta phase in these thin layers. So it does affect the transformation characteristics, and so we had to basically define what these are for our own purposes. And what this shows is that at around about 500 to 550 degrees C, you more or less get fully transformed into a steady state condition after about 10 hours. Now, this sluggish transformation is one reason why there's been a lot of ambiguity over the years on the zinc niobium phases. As you can see here, here's a lot of reported compositions for different phases. And as you can see there, it's all over the map. There's a very, very large spread. And the fully equilibrium, stable phase state should be a fixed composition. But if you have various heat treatments, varying times, you'll get a whole range of different compositions. So one of the more interesting studies more recently I was involved in is in the isolation of the stable zirconium niobium iron phase. And based on our studies, it turns out that rather than being based on ZrNbFe2, it looks like a better designation for that phase is NbZrFe2. So niobium itself is a strong Lavis phase producer. So the common Lavis phase in niobium iron alloys is NbFe2, which is a C14 hexagonal close packed structure, whereas ZrFe2 is a FCC structure. So here we have also the ZrNb2Fe phase down here, but a better designation for the other phase, which is hexagonal, is NbZrFe2. I'd like to finish now very briefly talking about hydrides. Hydrogen is very important because it's taken up, from corrosion, you get a lot of hydrogen ingress into zirconium alloys, and you get hydrides formed. And these hydrides can be very brittle and reduce the fracture toughness of the material, and also lead to a thing called delayed hydride cracking, which I will talk about later. So there's been quite a bit of controversy about the hydrogen phase diagram, but what seems to be commonly, certainly for pure zirconium now, is that there is 3 phases, and these are defined here: the gamma, the delta, and the epsilon phase. One of the peculiarities of hydrogen, just like with the niobium, we have this sluggish transformation. There seems to be in hydrogen a problem with the phase boundary. So when we're looking at the phase boundary here, what do we have when we're going to create some other hydride? The point at which we get precipitation or dissolution varies depending on if we're heating. The dissolution temperature is higher than if we're cooling and forming precipitation. So this split is common in zirconium alloys, and it may be just simply a kinetic thing, but there are many different theories about why that is present. You just have to know that it is. There is what's called a TSSD value and a TSSP value.